Okay, we're going to do an introduction to related rates today. We're just going to practice setting the problem up. We won't solve the problem until next class. Okay, to start, we're going to draw a picture. We're going to label the variables and constants. Then we'll write an equation relating the variables, and then we'll find the derivative doing implicit differentiation, and then we'll talk about why they're called related rates, because they're related. Okay, let's consider this scenario. Okay, there's a police car. They're approaching a right-angled intersection from the north. This should have a comma, grammar. A police car approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner and is now moving straight east. Okay. Let me draw a picture first. Okay, so there's a police car. Let's see, he's up here. Okay, he's chasing another car. So he's going this way. The speeding car has already turned the corner and is now moving straight east. East is this way. Okay, so let's consider this. Okay, police car is going down here. The other car he's chasing has already turned and started going east. So the other car is over here somewhere. And this is a right angle right here. Okay, let me read that again to make sure I'm okay. Okay, police car, he's approaching the right-angled intersection from the north, he or she. So he's from the north, he's coming down. He's chasing a speeding car that has turned the corner and is now moving east. There's the speeding car. Okay, now the police car has a certain rate because it's going this direction at some rate. This car has its own separate rate. I don't know who's going faster than who. We would only find out if we knew the end of the scenario. But I want to set up an equation to relate their rates together. So to start off, I just wanted an equation that is going to relate their distances, and then I can compare their rates. So I'm going to close this triangle, because if I close the triangle, I can relate this because I can see a right triangle there. Okay, I'm going to go ahead and call the distance from the police car to the corner, let's call it Y, just because it's going in the Y direction. You could pick any letter you like. Okay, the car that is being pursued is going this way. I'm going to call it X for no particular reason. Okay, I'm going to call the hypotenuse Y. And if you consider this, this distance here is also changing because as this car goes this way and this car goes this way, the rate of change of Y is changing too, as is the Y value. Okay, why did I call that Y though? Let me call that Z. Okay, based on the way I have this set up though, I know that the Pythagorean theorem is true because of the right angle. And I want to start with something I know to be true. Okay, this is a true statement about the picture I've drawn. X squared plus Y squared does equal Z squared because of the right angle. Okay, so I drew a picture. I labeled the variables X, Y, and Z. I want to write an equation relating the variables. Okay, so this is my equation relating the X, Y, and the Z. X squared plus Y squared does equal Z squared. Okay, now when I want to find the derivative implicitly, but let's look at what we're actually trying to find for the related rates. Okay, I'm going to find an equation that shows the related rates of the vehicles with respect to time, because their speed is their location over time, not their location. You know what I mean. Okay, so when I do the derivative, I'm doing it with respect to time. And for most of these related rate problems, it will be with respect to time because the rate is dependent on as they move the time. Okay, so this is implicit differentiation, but I'm doing it with respect to time every single time, which means I have to keep that in consideration. So if I do the derivative of x squared, I get 2x, but I'm deriving x with respect to time, so I'm going to put dx dt here. Okay, now I'm going to do the derivative of y squared. Derivative of y squared is 2y, but I'm doing the derivative with respect to time, so I'm going to put dy dt. And then derivative of z squared is 2z, and I'm doing the derivative of z with respect to time, which means I have to times it by dz dt. Okay, this is an equation that shows the related rates of the vehicles. If I had the values here, I could plug them in and solve for the missing values, but we're just doing this setup. Okay, let's go ahead and consider another problem and try to set it up the same way. Okay, example 2. An airplane is flying on a horizontal path that will take it directly over an observer. So where's my airplane? Okay, here's my airplane. Okay, he's flying on a horizontal path, and it's going to take it directly over an observer. So there's my observer down here somewhere. Okay, there we go. Something like that. The airplane maintains a constant altitude. So what is this? This is constant. Relate the rates of change of the distance between the observer and the airplane. Let me draw the observer to the airplane. And the horizontal distance between the two. Okay, this looks like Pythagorean theorem again. They're not all Pythagorean theorem, but these two happen to be Pythagorean theorem. Okay, so horizontal distance between the two is this one. Let's give it a letter. I'm going to call it x because horizontal makes me think of x. Okay, on this side, distance between the two. Any variable you like, I'm going to go with d for distance. And this is some constant value. I don't know what the constant is. It might be 1,000 meters. It might be 200 meters. I don't know what it is. Okay, but just initially, I'm just going to set up the relationship using the Pythagorean theorem. So this is x squared plus some constant squared equals d squared. Pythagorean theorem again. Okay, I want to find the related rate of change. It's going to be with respect to time because the plane is moving as time goes by with respect to time. So let me go ahead and find the derivative. So the derivative of x squared is 2x. Since I'm deriving with respect to time, I'm going to do times dx dt. Okay, now this is some constant squared. I don't know what it is. Maybe it's 10. If I do 10 squared, I get 100. The derivative of 100 is 0. The derivative of any constant is 0. So the derivative of this is just 0. So I no longer care about it. Okay, the derivative of d squared is 2d. And then with respect to time, dd over dt. Oh, I shouldn't have put d. That's rough. Okay. Okay, let's simplify this a little bit. I could divide the 2 out of here to make it a little bit nicer. But I do already have a relationship set up that I could solve if I had given values. Okay, so this is fine the way it is. This is relating the two rates of change or related rates. This is also doing the related rates as well. Man, that's a D. This is a hard day for me. Put the D back. Okay, and then the next class we'll actually start solving them.